Welcome to Spring LIB.
In this question, we are looking at the decay of a pion into a positron with its neutrino. And we want to find the kinetic energy of our positron. So a big clue that was given in the question is that the pion starts off at rest, right? Decays from rest. That is, its momentum is 0. So this tells us that the final momentum of our system over here must be 0 as well. So we're going to use two conservation laws in order to solve this question. First is the energy conservation and then the momentum conservation. Now first off, let us start off with the energy conservation. So the energy conservation tells us that the initial energy, that is just the rest mass energy of our pion, is equals to the final energy, right? The total final energy, that is the energy of the positron plus energy of our neutrino, right? And we're gonna go one by one to find out what they are. We know that energy of the electron is equals, right? E square is equals to momentum times c square plus m square c4, right? This is from Einstein's energy to mass relation. On the other hand, for the neutrino, because it is massless, it is simply the momentum times c square, right? No m square c4 because m of the neutrino, we are assuming it to be 0. Next, we're going to use the fact that the momentum, or the momentum of our electron, must be equal and opposite in direction, so equal in magnitude to the momentum of our neutrino, right? In order for them to be able to cancel each other out to have a total momentum of 0 by conservation of momentum. Right, so conservation of momentum. So this is very important over here. With this information, we will be able to actually substitute, right? Substitute that this thing over here is equals to momentum of the electron squared times c squared as well, right? Since momentum are the same and c is just a constant. Now from here, we can continue to simplify it further by substituting what is momentum of electron times c squared by rearranging the equation on the left hand side. So this is energy, total energy of the electron minus the rest energy for electron squared. Alright, and from here, what we can do is to utilize the energy conservation law over here to substitute what is EV square. So from here, we know that EV is pi c square minus energy of electron. So squaring this must be squared as well. So we will get Substituting this expression into our equation over here, we see that it will be a bit messy. But we will be able to simplify it quite a bit afterwards, because you see that we have the energy, total energy of our electron to appear on both sides, right? So it means that we can cancel this out. And what we have left, the only unknown variable would be the energy of our positron. And this is very easy to find, right? So what we have to do, we just rearrange the equation, bring this to the right hand side. Divided by 2 times of m pi c square. Alright, so this is our expression over here, which we should be able to simplify. So the mass of the pion, the mass of our positron is the same as mass of electron. All of this can be looked up on the table, right? 32-2. From here, now we know that the kinetic, we know the total energy of our positron. We can split them up into the kinetic energy of the positron plus the rest energy of our positron. And to find the kinetic energy, we just have to take the total energy, subtract away the rest energy. So the total energy can be found from the previous expression. Subtracting the rest energy, we should get value of 69.3 MeV. Right, this is after substituting in the rest energy of the pion to be 139.6 MeV. The rest energy of the electron or positron is 0.511 MeV. Right, and that's all that we really need in order to get this answer over here.